So in our continuation of talking about solubility and solubility curves, we've looked at the fact that solids are more soluble at high temperatures and gases are more soluble at low temperatures. And this stems from the solubility curve graph that we looked at in the previous video. So the higher the temperature of a liquid, the better solids dissolve. The lower temperatures of a liquid, the better gases dissolve in a liquid. And also, gases are more soluble under high pressure. And this is something that we're going to refer to as Henry's law. Now, when you get a pop out of the vending machine, a Coke or a Pepsi, the bottle is rather hard until you open the cap and let the pressure out. The reason they pressurize the sodas is to keep the gas, the carbon dioxide gas, soluble in the liquid so the pop doesn't go flat. If they didn't pressurize it, the gas, the carbon dioxide, would not be soluble in the liquid and the pop would be flat, as we call it. So we keep it under high pressures. And Henry's law is the law that tells us the higher the pressure, the more soluble that a gas is in the liquid. And carbonated beverages is a good example of that. Another example of Henry's law is something called the bends. And the bends is a disease that occurs in scuba divers, because when scuba divers dive deep under the water, let's say they're going down 50 to 90 feet in the water, the pressure of the water increases. And we have gas in our blood. We have nitrogen gas bubbles and oxygen gas bubbles in our blood that gets taken around to our bodies. Well, when it's under extreme pressure, remember the volume of the gas bubbles decreases. And then as the scuba diver comes back up to the surface, the pressure decreases and the volume of the gas bubbles expands. Well, if those nitrogen bubbles in our bloodstream expand, they can get caught in our joints and cause something called the bends, which is a very painful condition and can even lead to temporary paralysis if they get lodged somewhere in the spinal cord area. And that's a disease and a substance that you could look up later on. But those are some examples of Henry's law at play. So solubility of most solids increases with temperature. There are a few exceptions, yes. The rate at which a solid dissolves increases with increasing the surface area, meaning we crush it up, it dissolves quicker. Solubility of gases decreases as temperature increases. And the solubility of gases increase with the pressure above the solution. This is referred to as Henry's law. So these are all the trends that you need to understand in terms of gases or liquids, or gases or solids being soluble in a liquid solution. So if we want to dissolve solids, it's best to heat them and stir them and get them into small particles. And if we want to dissolve a gas in a solution, it's better when the solution is cold and when there is very high pressure. Again, just kind of a summary of all the solubility information that we've discussed. So enthalpy of a solution, think of enthalpy as energy or heat. And whenever a substance dissolves in a solution, it either releases or gives off heat. If you've ever used hand warmers, where you get like a plastic pouch and it's got a chemical in there and you break it up and swish it and it becomes hot. And sometimes we put them in our gloves in the wintertime. This is an example of an exothermic reaction and an example of enthalpy of solution, because heat is released when the substance is absorbed in the water. Sodium hydroxide is an excellent example of this. When sodium hydroxide dissolves in water, it's an exothermic process. It releases heat. So when something's releasing heat, we say it has a negative enthalpy of solution, because it's giving off heat, it's losing energy. When something absorbs heat, we say it's endothermic. And an example of these are cold packs. If you're doing an activity and maybe you sprain an ankle or get a bump or a bruise, the trainer will give you a cold pack that they'll shake up and it'll get cold that you can put on there. So this is an example of a substance dissolving in a solution that needs to absorb heat to do that. So it feels cold. We say it has a positive enthalpy of solution. Okay. So when a solid dissolves in a liquid, it either has to absorb heat or release heat in order for that action to take place. So it's either exothermic or endothermic. Exothermic means it has a negative enthalpy of solution because it's losing heat. Endothermic has a positive EOS because it's gaining heat, or it's absorbing heat. Henry's law, as we've talked about here, is the solubility of a gas in a liquid is directly proportional to that pressure above the liquid. So the higher the pressure, the more soluble that gas is going to be. There's a vocabulary word called effervescence. Perhaps you've heard of it. When you open a pop bottle and you get the bubbles that come up rapidly and the little spritzels that come off the top, that's referred to as effervescence. It's rapid escape of a gas from a liquid. Sometimes you see those Alka-Seltzer commercials on TV when you drop them in and the bubbles all start to go. That's an example of effervescence. So again, temperature's effect on solubility. You can see the importance of knowing this because we keep bringing it up. So then concentration. Concentration is the amount of solute in a solution. The more solute we put in a solution, the higher the concentration, the lower the concentration. And there are a couple ways that we describe concentration quantitatively in chemistry. One of them is percent by mass. And usually you'll see this on medications or over-the-counter products that you buy at the drugstore. What percent is the active ingredient by mass in the substance? And this is nothing more than just calculating a percent, which we all know how to do. Sometimes you'll see a concentration labeled in parts per million or parts per billion. And this is simply what it states it is. How many parts per million parts is the contaminant, or parts per billion parts? The one that you're going to see most often used in chemistry is something called molarity. And molarity, as we're going to see, is a calculation of moles per liter. And we're going to go through those concentrations here in a second, as well as molality, which you won't see as much, but will pop up on occasion. And here's an example of a data sheet given by a water filtration plant. Every year, the city is required to provide its clients with the regulated substances that are in our city water. This isn't the one from Fort Wayne, but your parents in every household in the city do get a readout like this every year, which says which tells us how much nitrates or fluoride or barium is found in our drinking water, and shows us that, hey, it is within legal limits. And these are always usually labeled in parts per million or parts per billion. So for molarity, as I talked about just a little bit ago, molarity is designated with a capital M, and it is the moles of solute over liters of solution. So we need moles and we need liters, and that'll give us the concentration in molarity. Please know this equation. You will use it quite often. So moles of the solute, this is the substance that's being dissolved, over liters of solution, the total combined volume. So the liters includes the solute plus the solvent. So when you see a substance that says like 2 molar HCl, and you've seen these labels in the lab so far this year, this literally means that we have taken 2 moles of hydrogen chloride and dissolved it in 1 liter of solution. So 2 moles per liter. And obviously the larger that number of molarity, the more concentrated the solution is. So here's an example of how we can do this. Question is, find the molarity of a 250 milliliter solution containing 10 grams of sodium fluoride. So we need to convert these into moles and liters. So the first step is to take this 10 grams and convert it into moles. Well, we know how to do that because we've done that quite a lot of times this year. So the molar mass of sodium fluoride is 41.99 grams. So we're going to divide the 10 by that molar mass, and we're going to see that this is equivalent to 0.238 moles of sodium fluoride. Now we're simply going to take those number of moles, 0.238 moles, over the number of liters of solution. Now 250 milliliters is equivalent to 0.25 liters. And we know that because there's 1,000 milliliters in 1 liter. So please make sure you have your numbers in the proper units before you put them into the molarity equation. So we have moles per liter, and we would see that this is equivalent to a 0.95 molar solution of sodium fluoride. So again, we converted grams into moles and milliliters into liters, all of which we know how to do, and then take the number of moles and divide it by the number of liters given. And that gives us our molarity. Again, the higher the number of the molarity, the more concentrated the solution is. Here's another example. How many grams of sodium chloride are required to make 0.5 liters of 0.25 molar sodium chloride? Okay, and this is an example of a calculation that we have to do quite a lot in the lab in order to make the proper amount of solution in the proper concentration. So I need to figure out how many grams of sodium chloride we're going to have to put in. So what I'm going to do is I'm going to start with the number of liters, 0.5 liters. And since I'm given 0.25 molar, that means I need 0.25 moles per liter. Right? 0.25 molar is equivalent to 0.25 moles per liter. Well, I want to cancel out liters, so I'm going to use that molarity conversion in my unit conversion. That way I can cancel out liters and go to moles. Now that I have my answer in moles, I can use that to convert to grams. So this is an example of a way to use a given molarity to determine how many grams of sodium chloride we need to measure out. Because our balances only measure in grams. Our balances don't measure in moles. So we need to determine how many grams of sodium chloride we need to dissolve in that 0.5 liters in order to make this proper solution. So I've converted liters to moles using molarity, and then moles to grams. 58.44 grams is the molar mass of sodium chloride off the periodic table. And so this tells me I need to dissolve 7.3 grams of sodium chloride into 0.5 liters of water to make a 0.25 molar sodium chloride solution. Now molality is moles of solute per kilogram of solvent. So this is a moles per mass equation, whereas molarity is moles per volume. Remember that 1 kilogram of water is equivalent to 1 liter of water. So if you're given volume of water, you can easily convert it to kilograms. Molality is designated with a small m. Molarity is designated with a big M. So here's an example. Find the molality of a solution containing 75 grams magnesium chloride in 250 grams of water. So my first step, as anything, is to convert grams to moles, which I'm using the 95.21 molar mass of magnesium chloride. So I have 0.79 moles of magnesium chloride. Now I'm going to take that moles per kilogram. I'm given 250 grams, but we must convert that to kilograms for molality. So it's 0.25 kilograms. So 0.79 divided by 0.250 kilograms. And that's equivalent to 3.2 molals of magnesium chloride. So similar calculations between molarity and molality, but they measure different units. Molarity is designated with a large M, molality is designated with a small m. Please remember that difference.